Hey everyone, and welcome back to this class, Artificial Intelligence, Reinforcement Learning in Python. In this lecture, we are going to discuss optimal policies and optimal value functions. As you'll see, they are interdependent, so we'll need to discuss them together. This is a key concept in this course, and as you go through the course, you'll realize how much depth there is to this idea. We can talk about the relative goodness of policies. Let's say we have two policies, pi1 and pi2. We can say pi1 is better than pi2 if the expected return of pi1 is greater than or equal to the expected return of pi2 for all states. Because we can talk about the relative goodness of policies, and one policy can be better than another policy, then we also have the notion of the best policy. In reinforcement learning, we call this the optimal policy. We use the symbol pi star to represent it. The optimal policy is the policy for which there is no greater value function. We can write down the optimal value function as the max of the value function over all policies. Note that optimal policies are not necessarily unique, but optimal value functions are. You can imagine how two policies can lead to the same rewards, and hence lead to the same value functions. But if you have one value function that's greater than another value function, then the optimal policy will be the one that leads to the greater value function. We can similarly define the optimal action value function as the max of the action value function over all policies. Because the optimal action value function is with respect to the optimal policy, we can define it recursively in terms of the optimal state value function. The state value function and the action value function can be related in this way. The state value function means that we are always choosing the best actions, and therefore choosing the max over all actions from Q. Notice how Q leads to some practical advantages during implementation. If we only have V of S, then what we have to do is try all the possible actions A to take us to the next states so we can get the values for those states. But if we have Q, we can directly choose the best action over all actions A from Q. Let's continue manipulating our equation for V star. We call this the Bellman optimality equation for the state value function. Notice how it's very similar, but not exactly the same, as the Bellman equation. We can do a similar thing to get the Bellman optimality equation for the action value function. One last thing to talk about is, once we have the optimal value function, how do we implement the optimal policy? The key point is the value function already takes into account future rewards, so nothing extra needs to be done in order to optimize the total expected future reward. All we need to do is choose the action that yields the best value for the next state. Notice how, for the state value function V, we need to do a look-ahead search, because V itself does not depend on A. So implementation-wise, we need to do all the possible actions A, look at what state we arrive in, S prime, and choose the one that gives us the largest V of S prime. If we have Q of SA, we can do this lookup directly. What Q of SA does then is it effectively caches the results of all one-step ahead searches.